So using logs to figure out relationships between pieces of data that maybe aren't traditional line, sort of linear relationships, is actually a really nice extension of logs. So this example's come from the textbook, but I figured it would just be a good way to talk through the problem with you. So here we are, we have some cities ranked according to the size of their population, and we've got their relative population to two significant figures below. If we plot that information, like so, we get not a straight line relationship between this information. We get something of a different sort of relationship here. So this is kind of, against its rank, I'm absolutely destroying this. Kind of bending more. It's got a curve to it, which suggests, to me at least, that its rank R is related to its population, we could say, by some other type of relationship. Some power of x. So it's perhaps a quadratic or a quartic relationship, or some other kind of obscure powered relationship there. Certainly not a line or anything immediately obvious to us. So we're told that the relationship is R equals A P to the power of n, where A and P are some sort of constant. So it's some sort of curved relationship, if you like. That's a really bad way of describing it, but you get the idea. But we've now got to figure out what A and N are. Like, what's the power on it? What's the scalar? You know, how do we take a standard graph that we know and stretch it so that we end up back at that relationship we had previously? Well, not easily, unless we're prepared to take logs. So let's do that. What I'm going to do is I'm going to take a log base 10, so I'm just going to write it as log, of either side of the equation. So we get log R equals log A to the P, AP to the N. So don't forget, you can only apply logs to the whole of both sides of equations. You can't apply logs to multiple terms. So if this had been, say, R equals N plus P, that is not the same as log R log N plus log P. That's utter rubbish. Don't ever do that. That's disgusting. Doesn't make any sense. All we can do is apply a single log to the equations. So you get log of the whole thing equals log of anything else on the other side. So now we should be able to just rearrange this log a little bit. I'm going to leave the log R on its own. When I've got multiplied interiors to a log here, I could rewrite that as log A plus log P to the N. And now I've got a power on a log that's separate from everything else and all that kind of jazz. So I can actually write that as log A plus N lots of, let's try that bit again, log P. So pulling that power down as a multiple instead. It's just standard log rules there. That should then give me, I'm just going to try and get rid of, oh no, I'm not going to be able to, darn. That should then give me something more of an expression that I recognise. So I'm going to call this a variable. I'm going to just imagine that was y for a second. And this one is x, in which case I've got y equals something, let's call it c, plus n lots of x. That's a line. I've got a linear relationship now. So in order to figure out what the values of log R and log P are going to be, and therefore be able to get what my intercept is and what my gradient is, I'm going to need to convert my R and P values from the question here into log R and log P. So I'm just going to do that purely by chucking all of those values into the calculator. So log 2, don't forget there's a log button on your calculator, and we're using log base 10 here. That's 0.30 to 2 decimal places. The next one would be log 3, and that is, let's jot that in my calculator, 0.48, and so on and so forth. So we're just chucking each of these terms individually into the calculator and getting the equivalent log value out. So here are all of those values. Now what I've done, is I've plotted all of those values on Desmos. So the red dot over here, those are each of those points. So there's that 0.3, the 0.48 we worked out a minute ago. These are the remaining, what will now be log R values, and these Y values are our log P values. As you can see, these are plotted out into a pretty much straight line. And not quite straight because we've rounded lots, like there's loads and loads of bits of rounding going on, all sorts of other stuff. But we've now got a linear relationship within which that we can figure out what our gradient would be. So what I've done here is a topic we're coming on to, we haven't done yet, but you might have done. This has given us a kind of correlation regression thing. So this is the extent to which these values line up to each other, that R value. But most importantly here, I've got a value for the gradient, M. So this is a topic we will come on to, so working out the equation of the line of best fit, but that's what this line is basically. It's a line of best fit or regression line. You will, for this stage at least, just need to read off of the graph to work out the equation of that line. So you'll be reading your gradient by picking 2 points that you know about on the line of best fit and reading the gradient off of them. So using the textbook and obviously zooming into Desmos to check this, I know that 5.68 matches up with 0.77 on the x-axis, and that 6.16 matches up with 0.05. So I'll use those two values, they both sit on my regression line, to calculate a gradient here of minus 0.67. So that works to 2 decimal places from what Desmos has calculated as the gradient of the regression line. And then to find the y-intercept, well, we've been given it here, but in reality what you would do is go and look at the y-coordinate and read that off of your graph as well. So there's your y-intercept, that additional log A that we had before. It's worth mentioning that you can actually apply this sort of technique to any sort of powered or exponential relationship between things. So here, instead of having a constant to a power, so some sort of polynomial, I've got something more like an exponential relationship. But I can apply logs to both sides, just like I did before. AB to the power of x. I can split up that right hand side log into log base A plus log base B to the x, and use the third log rule or first log rule, depending on which way around you order them, to give you x log b. In which case we're now plotting our linear relationship will come from plotting log y against x. Our intercept is going to be log base A, and our gradient this time will be log b. But that's because it's a different relationship to start off with. In summary then, if we've got either of these two types of relationships, so one where we know it's not already a linear relationship, it's some sort of curved relationship and we need to figure out what that is, we can apply logs to get a straight line relationship by plotting log r against log p or log r against p respectively, depending on the type, to be able to figure out what the constants a and n or a and b are respectively. So we would take logs of both sides, that means apply the log function to both. We would use log rules to split those up into a sort of more line-like, if you like, relationship. So we've got something plus so many lots of something else. That would give us, in this case, n lots of log base p, and so in this case we're plotting log r against log p, and that's where we then went to find our table of values, plotted all the values onto a new line and used the line of best fit. In the other cases it's exactly the same technique, just a different structure of equation. So I would have log AB to the P, log R equaling log A, so there's my y-intercept, plus log B to the P. And so in this case, my y-intercept, as I said, is log A, and my gradient I can already say is log B. So I would be plotting the equation log R against P in this case, and I can automatically read off what my y-intercept and my gradient are of these lines, and hence what the original variables constants A and B would have been. I'd totally recommend some practice on this. The Edexcel textbook is really great. The exercise that follows this example, so right at the end of the textbook, is brilliant and has all the answers, so that's really helpful. Good luck.